All right, so this is Precalculus, section 3.1, linear functions and their properties is the title. So I want you to take a moment and just we're gonna freestyle here for a second. Everything we know about linear functions. What do we know about linear functions? Let's engage our prior knowledge. All right, so linear functions. It's a line. It's got, when you have two linear functions, you can either have one solution, no solutions if they're parallel, infinitely many solutions if they are right on one on top of the other. It's got x-intercepts unless you're a horizontal line. The parent function is f of x equals x. We've got y equals mx plus b is point slope formula. Y minus y1 equals m times x minus x1 is point slope formula. And the slope equation is y2 minus y1 over x2 minus x1. And we've all learned that already. That's your prior knowledge that we are accessing, which is a teaching tool. All right, so if we want to graph linear functions, I'm not going to lie to you, I'll tell you all my tricks. All right, so we're going to graph linear functions. To graph linear functions, we need to remember the slope-intercept form of our linear function is f of x equals slope times x plus y-intercept, mx plus b. And because I'm really good at solving equations and doing algebra manipulation, this is really the only one I had memorized for a really long time, like a decade. Because then I would throw things in there and solve for the intercept, or vice versa. I'd throw points in for x and y and solve for the intercept. So we're going to graph this linear function together. F of x equals 2/3 x plus 1. We need to identify the slope, which is 2/3, and the intercept, which is 1. This should all be really familiar. If it's not, then welcome Algebra 1 students. So we start at our intercept, which is at 0, 1. We put a little dot there. And then we apply the slope. We go up 2/3. And here's our up 2, which is our change in y. Remember, I think we talked about this last chapter. Delta means change. So if you see that little triangle, that means change. You guys are old enough now where we're starting to use terminology. That's big boy math terminology. So change in y is 2. Change in x, or delta x, is 3. And then we draw a line through those points. If I'm hand graphing this, I go as many points on my graph as I can to make sure my line remains accurate, because sometimes it's really easy to get off kilter. So I put as many points on there as possible. So change in y over change in x is 2/3. The y. Okay, that's as hard as graphing a linear function gets. You can always use point slope if you're given a point and the slope instead of the slope intercept. It all ends up the same. You just would start at the point that you're given and apply the slope from that point. You can graph it. All right, average rate of change to identify linear functions. That's our second learning objective. The first was to graph linear functions. Now we're using average rate of change. I promise you, we're just renaming something we already know. The average rate of change is delta y over delta x. What is the other word we've been using for that? yeah, delta y over delta x is slope. It's also known as the average rate of change. So it's not a new concept, but we are calling it something a little bit different. And we do this because in science, we look more at average rates of change, and in engineering and in physics. So when you have an input, a function, to calculate the average rate of change, you take the and minus the outputs over the difference of the inputs. So in this case, it would be -3. And if you do that between -1 and 0, 0 minus -1, and you actually, I don't want you to write this down yet. Do not write this down. We're going to do it together in a word problem. So if you go -1 minus -2 over 10 minus 13, and you get -3 over 1. And if you have a linear function, your average rate of change should be constant over the course of your line. Okay. Linear functions have a constant average rate of change. It's kind of important. Please write that down, because there'd be like a little quiz question that says, true or false? Linear function have a constant average rate of change. Or true or false? Linear functions do not have a constant average rate of change. You have to know that. That is, the average rate of change of a linear function f of x equals mx plus b is delta y over delta x equals m. So our slope is equal to the average rate of change, and for a linear function, that is constant. For linear functions, that is constant. All right, so our first example problem. I'm going to read through it. A strain of E. coli BU 397 Res A 441 is placed into a petri dish at 30 degrees Celsius and allowed to grow. 30 is pretty warm because room temperature is usually 25. So 30 is 5 degrees Celsius above room temperature, so it's like swarmy, swamp conditions. The data shown in Table 2 are collected. The population is measured in grams and the time in hours. Pull out the ordered pair x comma y in the Cartesian plane and use the average rate of change to determine whether the function is linear. Okay, so let's put a nice little graph on our paper. We're going to count by ones on the x-axis, and we're going to count by 0.1 on the y. And then go put a nice little graph. So our hours in time is on our x, and our population is in y. I'm not sure why they didn't start this over here at 0, but I'm okay if you start yours at 0. Okay, so given the graph and the data points, we're going to calculate the average rate of change between 0 and 1, 1 and 2, 2 and 3, 3 and 4, and 4 and 5. They should be, if it's a linear function, our average rate of change should be constant. So if you go 0.12 minus 0.09 divided by 1 minus 0, you get 0.03. If you do that same process, 0.16 minus 0.12 over 2 minus 1, you get 0.04. 0.22 minus 0.16 over 3 minus 2 is 0.06. The next one is 0.07. The next one is 0.10. Go ahead and make sure these are on your, next to your data table, the average rate of change. Make sure you write average rate of change to the right-hand side of your table so that you can track it back. And we see average rate of change is not constant for this function. Since the average rate of change is not constant, then the function is not linear. All right, so the next example is the data in Table 3 represents the maximum number of heartbeats that a healthy individual should have during a 15-second interval of time while exercising for different ages. Plot the ordered pair x, y in the Cartesian plane and use the average rate of change to determine whether the function is linear. All right, so the first thing it asks us is to graph the function. And so we start at 20 on the x-axis and we count by tens. And this is why 20 is not exactly on the origin, because we can't get a y-intercept out of that unless we want to put the other two intervals down there. So if we count by tens on the x-axis and by fives on the y, and we plot these points 2, 50, 30, 47.5, 40, 45, 50, 52.5, 60, 40, and 70, 37.5. So from the looks of this graph, it looks linear, but we're going to have to prove that by writing down the average rate of change. All right, so when we take our first point and we go 47.5 minus 50 over 30 minus 20, we get negative 0.25. And if you look, the difference between 47.5 and 50 is negative 2.5. We're going to continue that difference being 2.5 for each of these, and then the change in x is 10. So 2.5 divided by 10 is going to give us 0.25 for each of our delta y over delta x. So because our average rate of change is constant, we can say that this is a linear function. It's all negative 0.25, I promise. All right, our third learning objective for this section is to determine whether a linear function is increasing, decreasing, or constant. Okay. We are going to tell if a function is increasing, decreasing, or constant by looking at its slope. If slope is positive, so if I'm writing this in my notes, I'm going to hit enter right here. Increasing if slope is positive, then I hit enter again. Decreasing if slope is negative, then I hit enter again. And constant if slope is 0. So when you write that in your notes, I would write it like this. I would separate it. I definitely, for my brain, would need it on separate lines. So I would put an enter in between each of these items. right, let's look. Let's see how this looks. We are going to A, B, C, and D. Take a look at these linear functions and determine whether they're increasing, decreasing, or constant, and it will be fast, like it'll be lightning round. F of x equals negative 2x plus 4. Our slope is negative, so it's decreasing. G of x equals 5. What's the slope on that? Not 5. The slope is 0. Because when you just get a number, that's just the intercept, so that means your slope was 0 and it canceled out the x, or made the x ineffective. Okay, so for C, S of t equals 3/4 t. Has a slope of 3/4, so it's increasing. And last but not least, D, it has a slope of 1, so the function is increasing. So A is decreasing, B is constant, C is increasing. Oh, sorry, this is decreasing, constant, increasing, increasing. All right, last learning objective, build linear models from verbal descriptions. This is the hardest task in this section because it's very word problem-y, very word problem-y. So when we're modeling a linear function, if the average rate of change of a function is a constant m, a linear function can be used to model the relationship between two variables. So I would probably not write this down because you guys have this written down already, right? So our example problem, the straight line depreciation. Oh, I take it back. We've got the supply and demand problem too. Book value is the value of an asset that a company uses to create its balance sheet. Some companies depreciate their assets using straight line depreciation. So the value of asset declines by a fixed amount each year. The older something gets, the less valuable it is, like a computer. That would be a company's asset. The amount of the decline depends on the useful life that the company places on the asset. Suppose that a company just purchased a fleet of new cars for its sales force at a cost of $28,000 per car. The company chooses to depreciate each vehicle using the straight line method over 7 years. This means that each car will depreciate by $28,000 divided by 7, or $4,000 per year. We're going to write a linear function that expresses the book value of each car as a function of its age. All right, so we're going to write a linear function. We're going to let b of x represent the value of each car after x years. We're going to let b of 0 be $28,000 because that's how much the value of our car starts. And the slope is negative 4,000 since that's what our change is every year. We're decreasing by 4,000. So the equation is b of x equals negative 4,000x plus 28,000. So anything, if you're looking in your problem, and this isn't true for every word problem, but for most of them, any item with a per and a time is probably your slope. So in this case, $28,000 per car doesn't apply to our slope, but the $28,000 is how much you start out for a value. So anything you start with, any amount you start with is your intercept, and then anything you get that can be per time is usually your slope. Okay, so we're going to graph this, and I would definitely count by 1,000s. on my paper. So the age of the vehicle in years is on the x-axis, and our book value is on the y-axis. We start at $28,000 and we depreciate until after 7 years our car is worthless. Okay. For C, what is the book value of each car after 3 years? So we're going to take our x value, we're going to plug in 3, and there's a nice little typo here. And then we're going to add 28,000. So let me fix my typo. I cannot fix my typo. I can't fix it. I can't fix the typo. But I tried real hard. You guys saw me. All right. Crisis averted. So if I plug in 3 into my function, I get out negative 12,000 plus 28,000 is 16,000. So after 3 years, the car is worth $16,000. All right, so let's interpret our slope. The slope is the average rate of change and is negative 4,000. So this means that for each additional year that passes, the book value of the car decreases by 4,000. When it asks you to interpret the slope, make sure you have a nice sentence using proper grammar, punctuation, spelling to describe, because they're asking you to verbally write out. When will the book value of each car be $8,000? So you set your equation equal to 8,000. We subtract 28,000 and we get negative 2,000 equals negative 4,000x. And then you divide by negative 4,000 and you get 5. So each car will be worth $8,000 when it's 5 years old. Awesome. Okay. Supply and demand, and I know this is definitely a quiz question that I put on your 3.1 quiz. The quantity supplied of a good is the amount of product that a company is willing to make available for sale at a given price. The quantity demanded of a good is the amount of a product that consumers are willing to purchase at a given price. Suppose that the quantity supplied S and the quantity demanded D of cellular telephones each month are given by the following functions. S of P equals 60P minus 900, and D of P equals negative 15P plus 2,850, where P is the price in dollars of the telephone. The equilibrium price, so get your highlighter out and highlight equilibrium price, because if we're going to be assessed on this, then it's important to know what that is. Of a product is defined as the price at which quantity supplied equals quantity demanded. That is, the equilibrium price is the price when S of P equals D of P. Find the equilibrium price of cellular telephones. What is the equilibrium quantity? The amount demanded at the equilibrium price. So we want to find when supply and demand are equal. So, and if I'm manufacturing something, that is kind of like our magic place. So we're going to set supply and demand equal to each other. 60P minus 900 equals negative 15P plus 2,850. I'm going to add 15 P's to both sides. to get 75p equal, and then I'm going to add 900 to both sides. And so 75p equals 3,750. So we added 15p's to both sides and added 900 to both sides. Then I'm going to divide by 75, and I get p equals 50. So the price of $50 is our equilibrium price. What is the equilibrium quantity? So we're going to plug that in to our supply equation. We get 60 times 50 minus 900. So this is 3,000 minus 900 is 2,100. So 2,100 phones are demanded or supplied at a price point of $50 a piece. I have to escape here, sorry. When they launch their phones from me. What's going on?
You want to see, no. Do you have multiple books on your Pearson account?
I have all like other one on the
Okay, so I have like chemistry on it. I need to add. They're trying to set me up for a different account for help. And can you just add it onto mine?
Because mine looks like it's like programs,
Yeah.
and then I'll have to add a program, and it may, because it's health versus science, like you may be able to have chem, bio, all their science stuff,
But since health science is science.
right, and math, it's not like the Precalculus book, even though it's the same manufacturer,
Yeah.
it's a different site.
Why? Let's do that. Let's just add it on there.
Yes, it is. That is obnoxious. I agree. Oh, we've been recording. Apologies, we've been recording. This audience at home, apologies. All right, so we're going to graph our two functions and label the equilibrium price. So S of P, if you so on our x-axis, we're counting by tens and putting the price, and on our y, we are putting our quantity. And the equilibrium point is where these two lines cross. S is equal, S of P is equal to D of P. Back to that. Come on, buddy. He's thinking. And there we go. And that's the end of our show for today.